Hi, this is Caitlin,
Nicholas Boyd.
and we're going to be explaining our project for assignment 1. This is the basic geometry where we have the vertical length of 10 millimeters and height of 500 millimeters, and the mesh setup established as the vertical sizing of 150, the horizontal sizing of 400. We face meshed, and then we did the name selections for all 4 of our edges. And then for the setup, Nicholas.
For the setup, our first flow will be the P flow. So we're going to use a laminar flow because that was what was asked for us. And then we are going to have an inlet velocity of 6 meters per second and then an outlet of 0, which we will show in a second.
Outlet of 0 pressure.
And both these plates are stationary, by the way, so they're just not moving at all.
And we made sure to change the model to a laminar viscous flow. And made sure that our air material was set to a density of 1 and a viscosity of 0.0001.
This will stay the same for all 3 processes.
The boundary conditions are what's going to change for our cases.
So we'll just initialize it, hit OK, and then we're going to run the calculation.
And to save time, we've prepped all of them beforehand.
Here on the graph, it's slowly converging. You just have to give it a minute until it's done. OK.
Then opening up our results.
Okay, so with our P flow, the max will be right in the middle, the max flow. So that's why it's very, very dark red right in the middle. And then as it goes farther out, it's a lighter color. And if we look at the chart, or the table, excuse me, chart first, it'll show us the max right there.
Yep.
And then table.
Oh, my table didn't save. It's fine.
We'll just input the max velocity. You just have to type in the little code.
Function CFD max val, establishing the u velocity at our end line, gives us a maximum velocity of 8.41 or 8.841 meters per second. And that is it for our explanation of case 1, case A.
Case B, we'll go to the C flow. Just give it a second. Let's get it set up.
The geometry mesh is staying the same as previously established.
The only thing that's changing again is our boundary conditions. For those boundary conditions, our inlet velocity will be 0, and same with our outlet, but the only thing that's moving is the top plate, and that's at 10 meters per second.
Yep, we changed our inlet to a pressure inlet instead of a velocity inlet, setting it to 0. Same thing with our outlet. And top plate being set
to 10.
To moving at 10. So, initializing.
We're going to run it.
And running.
It's going to slowly converge.
Nice and slow.
Click on our results. Takes a second to update.
There we go.
There we go. So our max velocity is at the top, as you can see with the red line. And it ends up actually being the same as our input for 10 meters per second, because there was no pressure gradient. So the speeds just stays the same.
Yep. Verified by our formula. Then our chart shows an almost linear velocity. And then last but not least, our combo flow.
Going straight to setup, because only our boundary conditions change. Okay. Then with this one, our inlet will be 7 meters per second, our outlet will be 0, but also our top plate will be 7 meters per second.
Yep.
So go to boundary inlet.
So inlet is now velocity inlet at 7 meters per second. And top wall is moving at a speed of 7 meters per second. Initialize and run. Wait for convergence.
So our max velocity is still kind of in the middle this time, but we do have a higher velocity, not higher than our max, but it's still pretty high at the top because of that top plate moving.
Yep.
There's
So it shifted the parabola up towards the moving wall. And shows that our max is 9.169 meters per second. And that's it.
That's